It's only within 2.5 months we have to wrap up, na? So this thing we have to consider also. This is not a normal semester going on when we have got enough time. Fine. So it is fixed on next Wednesday from 11 a.m. I will send a formal mail by this weekend. Fine. Let's start
Okay,
today's
sir.
class.
Okay. Okay, so we have the final topic, which is called recursion. There are some other topics which we skip for this course because we don't have enough time and we have to synchronize our course with the other batches. So we fixed our syllabus up to this recursion. Okay. So recursion, you are also familiar with the recursion. Let me, okay. You are basically familiar with recursion. So recursion is a computation. So we called a computation to be recursive if the nth parameter or the nth term of the function can be computed by the n-1 term of the argument. So simple example of recursion is something like this. If I want to compute the Fibonacci or series, like say f of n is 1 into 2 into 3 into something n. So this is called the Fibonacci. Sorry, this is called the factorial of n, or sometimes we represent these things in factorial. So how can we compute this factorial? So this factorial is simple. I can do by, if I have already computed the n-1th factorial, then I can compute the nth factorial by the same functions with a less parameter, with a lesser argument, and multiply it with n, and we can get the factorial of n. Okay. So similarly, there are other functions, like if we have a series, say n is equals to say 1 plus 2 plus 3 up to plus n, then this can also be simple n-1 plus n. Or if I have square terms, some things like this, then this is also represented in this form. So what we find that there are some functions which are recursive in nature. Recursive in the nature says that there is a, we will formally define what is the recursive in nature. The simple interpretation is that there is a function f which has to be computed with a parameter n. So this parameter n is the basic is the end computations of the function, and we call these functions to be a recursion if the f of n, or the f with a parameter of n can be expressed with the same functions with another parameter I, and I is less than n, or vice versa. You can also define it in a opposite sense. But if the function f of n can be computed with the function of f I, where I is less than n, then we can call this function as a recursive function. So that means the solution of f of n is basically depends on the previous computation of fi, where I is less than n. So these are the formal definitions of a recursion function. If I write a recursion functions, then I basically express the function in a formal way. So f of n is basically there are two part of the formal definitions. We'll come this part. But the first thing is that when n is greater than 1, then I can represent f of n is equals to n into f n minus 1. So this is the factorial function. And when n is 1, so this is called the termination of the base condition. The base condition says that if n is 1, then we return the function value as 1. Okay. Similarly, there is a Fibonacci numbers. The Fibonacci numbers are represented in the form of f of n is equals to f n minus 1 plus f n minus 2. And when the base condition is 0 and 1, then we return a 1. So Fibonacci series are in the form of like this. We represent f of n is equals to fn minus 1 plus fn minus 2 when n is greater than 1. And when n is less than 1 or when n is equals to 1 or 0, then f of n is 1. So the series runs in this way. This is the first element, so f of 0. This is the second element, f of 1. Then we have 2, so f of 2 is 2. Then f of 3 is basically the addition of the 2. So this is add of these things. So 3, f of 4 is the addition of these 2. So this is 5. And it keep on computing. So when we are computing the f of 4, then what we have to do? We have to compute, or we have to know what is the value of f of 3, and we have to know what is the value of f of 2. Okay? And when I try to compute f of 3, I try to compute what is the value of f of 2 and what is the value of f of 1. Okay? And in this way, there is a means one type of fallback, and then I accumulate the results, like say f of 2 is f of 1 and then f of 0, and we accumulate the result in this way, and I get the value of f of 4. Understand? So in this way, there are some functions which depends the value of this function, or the output of these functions depends on the previous arguments. Then we call these functions as a recursive functions. Yeah. So C programming language will give you a facility to design this type of recursive functions, where it looks like that if I have written a C function for this factorial, then the factorial itself calls the same functions. Means within the factorial, I am basically calling a same functions, like factorial n calls the factorial n minus 1, and then factorial n minus 1 is also calling the factorial n minus 2. In this way, I have a definitions, or I have a technique to write a recursive function in my C programming language. Okay. So before we look into the programming part, just take a mathematical formal definitions of this recursion. So every recursion function is having a base condition and a recursive call. So what is the base condition? The base condition are the condition where when the function returns, when the function is not calling recursive, when the function terminates, then it is called the base function. So in the factorial, the base condition is f of n when n equals to 1. It does not have any recursive call, so it returns. Okay. So we call this is a base condition, or the which the condition determines the termination of the recursion. Okay. And then we have a recursive call, or recursive definition. The recursive definition. So the recursive call is basically the recursive call is basically we are calling the same functions, or we are invoking the same functions with a parameter n, with a parameter which is less than n, and then we have a computation. So this is not only the f of n is calling the f n minus 1. So there is a computation associated with this recursive call. So in factorial, the computation is n into f n minus 1. So in Fibonacci, the computation is f n minus 1 plus f n minus 2. So in this way, we are basically having two types of conditions. One is called the base conditions, and another is called the recursive call. So before we go for any programming implementation of any recursive function, first we try to understand, or first we try to sketch out what are the base conditions and what are the recursive call. And once I have done these things, then my implementation of the recursion is very easy. Okay. Understand? So in such a way that the problem can be solved by the solutions of the same problems with a lesser parameter, or with a smaller parameter. So if I can design a problem in this philosophy, then this is called the recursive functions, and C will help you to design this function. Okay. So we'll take an example. The first example is how to compute the Fibonacci series. The Fibonacci series that we already described is the recursive function. The recursive calls are basically fib. So this fib n is fib n minus 1 plus fib n minus 2, and the base condition is when n is equals to 0 and 1, then we return some 1. Okay. So now, if we want to implement these things in a C programming language, then I have to design a function which will return an integer, and this function will return the which takes the argument as n. So n is the left hand side of this definition. So I am putting some value of integer n, and I am computing the nth term or the nth output of the Fibonacci series. So in my example, if I put say 4, then my Fibonacci will return 5. So if I put the argument as 5, then my Fibonacci will return the 5 plus 3 is 8. So in this way, the ith term or the nth term can be computed. Understand? So what is the implementation of this program? So if we get into the implementation part, then we'll find that this is the left hand side is the right hand side is basically the implementation of the Fibonacci. So what it does, it is simple. So just try to map the definition into my programming language. So the definition says that I have to write a program, or I have to write a function which has a prototype like this. It returns an integer and it takes an integer argument. Okay. And inside this program, I have to simulate this condition. The condition is that when n equals to 0, then I return 1. When n equals to 1, I have to return 1. So it says when n equals to 0, it will return 1, or when n equals to 1, then it will return a 1. Otherwise, what will return? It will return the Fibonacci n minus 1 plus the Fibonacci n minus 2. Understand? So otherwise, what will be the output of this recursion? The output of this recursion is that Fibonacci n minus 1 plus Fibonacci n minus 2. And thus what we have done in my Fibonacci function or the fib function is to realize these conditions. I have the base conditions, I have the recursive call, and I just simulate these things in my program. Just to keep in mind that before every recursion call is followed by the base condition. So the base conditions has to be checked first. If the base condition does not, or base conditions are not satisfied, then we go for the recursion. Okay. So if I write the recursion before the base conditions, then my program is basically erroneous, because base conditions are the termination part. So if you have to check whether your recursion will be terminated. Otherwise, you have to recur. Understand? And simply this function will be invoked in my main, and I will get the result. This 5 means I am looking for the 5th term of the Fibonacci series. I am not computing the Fibonacci 5, but the 5th term of the Fibonacci series. Yeah. So n is representing the 5th term. If we look into the series, then this is the first term or the 0th term, 1 term, 2nd term, and it will have a 5th term in the Fibonacci series. So this will be 8. Understand? Yeah. Okay. And then this argument I am passing to my recursive call, and my function will return the output of the function will compute the 5th term of the recursion, and it will give me the Fibonacci of 5. Understand? And we can print this part. Okay. You get this part? Yeah.
Yes, sir.
So this is another example where we are basically computing the factorial. So the factorial is in the same way. What is the factorial? What is the recursive definition for the factorial? It says factorial n is n into n minus 1 when n is greater than 1, and 1 if n is equals to 1. So this is the base condition, and this is the recursive call. And we have done the same thing. So in my implementation, I have the factorial of n. So I check the base condition. If n equals to 1, then we return the 1. Otherwise, I am returning n into the factorial n minus 1. So again, the factorial n minus 1 will be computed. It will check whether n minus 1 is equals to 1 or not. If not, it will call the factorial n minus 2. And the C programming, C environment will internally perform these things. You just remain calm and cool, and you will get the factorial in your result. Understand? So if I run the part, it will run with a factorial 4. So factorial 4. Yes, so we get the 24. That means the bar. Yes, 24 is the factorial 4. Okay. Understood? Get it?
Yes.
Okay. So, so think in other way. Don't go for a programming in the first attempt. You think the recursive. You think how I can design the recursion. Then you program the recursion in your implementation. Understand? So you sketch it, the base conditions and the other parts, and then you go for the programming. Okay. Understand? That is the main things in my recursion. So this is again okay. So now we try to understand that how these variables, how the scope and the variables will be working. Means I am calling a factorial n, then factorial n will call factorial n minus 2. Again, factorial n minus 2 will call factorial n minus 3. Then how these variables, how the results and how this computation will be carried forward and how the results will become. That things we try to understand. So means how the variables, how the values are basically handled by the C programming language or the compiler. So we try to understand in that sense. So recursion is a function which calls itself. So sometimes in your copy or in your books, you'll find that recursion is a function, it calls itself. So it is true, the function is calling a same function. But mathematically, we have the definition in different. So the computation of a function is depending on the computation of its lesser argument or less value of the argument. Okay. So when the function calls other functions, then what happens? As we understand, when a function calls another function, then the calling functions, its scope and its scope is invisible and its lifetime is valid. The called functions, it defines its own scope and the variables. Understand? So that same thing happens here also. So when the function is calling another function, the new set of variables are created in the called function. The scope only restricted within the variables. So you are not able to get access of the previous n. You are now having a new definition of n minus a new definition of n, and the value is n minus 1. So the previous call visibility is not allowed to you. Okay. And then however the lifetime of the previous value remains in the memory. So we'll show you in a diagram how it is. So if I just look into this part, then the scenario is something like this. When Fibonacci n is live, means when the first iteration is, or the first recursion is called, then we have a definition of the n in the first recursive function. Then we call the another function or the same another instance of the same functions with a parameter n minus 1. That means this n is not visible, but its lifetime is valid. Now we have a new variable which is in form of a n minus 1. Its lifetime is valid, its visibility is valid. Then again n minus 1 calls the same function with a parameter of n minus 2. Then again the n minus 1, they are not visible, but their lifetime is valid. Then we are having a new variable n minus 2. Okay, so in this way the function is 1. Then when the returns is happening, when the returns happens, then say I am returning from the function factorial n minus 1 to the function factorial n. Then everything in this function destroyed, and the return it returns the value something n and the local computations of these functions, understand, which will be available to the function n here. Okay. So let us try to understand how these things is happening. This is the simple example. So as we have already seen, the factorial can be computed with the base value. If the base condition is n equals to 1, then I have to return 1. Otherwise, I have to make a recursion call n into factorial n minus 1. Okay. Now think that I am executing the program with a parameter or with the n value equals to 4. So the main it set the initial call or the initial argument n equals to 4, and it invokes the recursive definitions, okay, or recursive function. Then what is happening? So this is the instances of the recursive functions because n equals to 4. So I have to in the first call factorial n, the parameter is 4. Clear? So now this we have a variable which is named as n, and its scope is visible, its lifetime is visible. Okay. Now these functions will call another factorial functions where the variable with the n equals to n minus 1. So it will be 3. So in my memory, when the first invocation is performed, then in my memory we have an instance which is n, and this value is equals to 4. Then what we do? We call the second function. We call the second instance of the function. Then the previous one is invisible. So n equals to 4 is now invisible, but its lifetime is valid. So now we are having a new set, a new variable which is n equals to 3. Okay, and then it calls the second one, so third one. So these two are invisible. Now we have a new function which is n equals to 2, and then it calls the fourth one. Now we have all these three are invisible. Now we have a function which is n equals to 1. Understand? And now what happened? This is the base condition means. So it returns. What it returns? It will return the value of 1. So it will return the value of 1 to its base. So what it does? When it returns this, it returns a value of 1, and this everything is destroyed. So nothing. So you see, in my memory, this variable was there. Now when it returns, this thing is destroyed. So now this one is coming from the return part. Okay? This one comes from the return part. Okay? Then what is the computation in the factorial of 2? The factorial of 2 is basically return n factorial n minus 1. So this is already available from the return. From the return, I get 1, and now I have to multiply this 1 with the current value of n, and I have to return it to the previous one. So now my current value of n is 2, and what is available from the return is 1. So I compute n is equals to 2, and then I will return to its calling function. Okay. So what it returns? It will returns 2 into 1, which is 3. Okay. And this thing is destroyed. This one is also destroyed. This thing is also destroyed. Now in this function, again we have a recursion call. Say factorial n, which will be n return n into factorial n minus 1. So n minus 1 already having the value of 3. Now the current value of n is equals to 3. So what we will return from this function to the previous function is basically n, which is equals to 3, and factorial n minus 1, which is coming from the return. So now we'll have 3 into 3, 3 into 2. So this is around 3 into 2, and now when this function returns to the calling function, it will return 3 into 2. Clear? And then this is the initial call. The initial call have to be returned to the main. Return to the main, which is n is equals to factorial n minus 1, and this n minus 1 is now having the value of 6, and this will be multiplied with 4, and that things will be returned to the mean, and finally these things will be returned to the mean, and mean is having the value of 4 into 3 into 2 into 1. Understand? Yeah. So in this way the calls are basically executed. So let me work it from the beginning. So this is the first call, n equals to 4. So in my memory we have a instance of n equals to 4. Clear? So when this function will return, so when this function will return to the main, what will it will return? It will return n into factorial, say 4 minus 1. I am just writing instead of this will be a confusion. So let it 4 into factorial 3. Yeah. And now I am calling the factorial 3. Yeah. So when we call the factorial 3, again this is invisible, a new instance of n is created, and now this function will again return 3 into factorial 2. Yeah. And now this function calls the factorial 2. So again all these things are invisible. Now I have to make a 2 into factorial of 1. Okay. And now this will call the factorial in things of 1. Now the base condition is met, so I return a 1. Clear? So when I return a 1, this memory is deleted and 1 is returned to the calling function. So previously it was 2 into factorial of 1, and factorial 1 is now available, so it is 1. So the value now becomes 2. So when it returns, this 2 is coming from this memory. So now you see previously this memory is not visible, now this memory is visible. So this 2 is coming from this memory. So this 2 is coming from this memory part. Now when the call returns to the n equals to 3, then again this memory will be deleted. So this memory will be deleted, this will be visible. So now this will be deleted, the things n equals to 3 is visible. But in this case, what is the part? It is 3 into factorial of 2. Now factorial 2 already having the value, which is 2 into 1. So we are getting 6 here. We are getting a value of 6 here. Understand? And then when it is also returning to the main, it returns the 6, and now n equals to 4 is visible to me. So I am able to compute 4 into 6, and then I will return to the main. Okay. Understand? Get it?
Yes, sir.
Okay. So this is the philosophy how we are calling. Means there is a step down. We are moving downwards in that step. It's like n minus 1, n minus 2. Say this is 1. So when we meet a 1, then I again move towards up. Yes? So that is the process of recursion. I am going deep, then I am again moving towards up. Okay. Okay. And if you think it how the memory will be organized, just apply the basic concept of the lifetime and the scope. Then it is easy to understand how the values are basically not colliding. Which the values are not ambiguous. These values are basically having their lifetime and the scope. So n equals to 4 does not collide in its subsequent calls. Yeah, it will be remain invisible. Okay. Okay. Achha, so there is a binary search. We'll discuss this binary search after some times. But before we go in for this problem, let us take another problem. Say I have a definition something like this. Say let I take the problem where we have to display the binary binary representations of an integer. So let the integer is say 15. Then the binary representations, how do we compute the binary representation of this 15? We basically divide this 15 by 2. Okay, so that this remainder is 1. Then we have 7. So again we have a 1. Then we have 3. So this remainder is again 1. We have 1 divided by 2. We have a remainder of 0. And this is the base condition. This is the termination. So if the value, the base condition says that if n equals to 0, we return. Okay, so this is the base condition. Otherwise, what we have to do, if n is greater than 2, we have to set n is equals to n minus 2, and we return 1. Return 1 or display 1. Okay, so the thing is something like this. So there is a recursion call. We call these things as a binary of, say, integer or decimal n. Okay. So now how can I design these things? The designing is something like this. We have to call if n is equals to 0, or we just return if n is equals to 0. Okay. We do not have any recursive call. We just terminate the call. Okay. But when n is not equals to 0, then what we have to do? We have to call it by it recursively n by 2, and then we print the n factorial of 2. Okay. That means, say what I am doing, say let we have 15. Okay. So if 15 is not equals to 0, then we have a recursive call. So what is the recursive call? I will call for 7. Okay. Understand? And when will come, I am writing, and I will print 15 modulo of 2 is 1. Okay. Then I call, so this is not equals to 0. Then I call for 3, and I will print again 1. This is not equals to 0. I call for 1. I will print 1. So this is not equals to 0. I call for a 0, and I print 1. Okay. Understood? This is the remainder. This remainder is basically 15 mod of 2. This is 7 mod of 2. This is 1 mod of 2. And this is again, this is 3 mod of 2. This is 1 mod of 2. Yeah. Now the thing is that this printing should be in the reverse order. So the printing should be, this will be the most significant. So this will play the most significant part. So this will play the least significant part. Understand? So my program should print the last one, print 1, then this print 1, or these are all 1. So let it be 14, then it will be easy to understand. So this will print 1, so this will 7, so this will print 0, and the rest of this. So my program will print 1, then this 1, then it will print 0, then it will print 1. Okay. But how can I do these things? I am calling the recursive function, say 14 first, but I have to print its corresponding argument at the end of all the recursions. So when I have to, since I have to start with n equals to 14, clear, I suspend my printing function. I call n equals to 7. I suspend my printing function. I'll call n equals to 3. I again suspend my printing condition. So when this printing condition will happen, when we'll return from the base conditions towards upward. Yeah. So when I'm returning from the base conditions, I have to print this one. When I am returning from the calling functions to the call functions, then I print these things. So how do we do these things? Clear? So this is simple to do. So there are two ways to design the functions. Say the first functions, I can design the recursion like binary to decimal or decimal to binary or binary of decimal, whatever the part. Say binary of decimal. Clear? And I put a n. Clear? The thing is that if I want to suspend, there are some functions or there are some executions which has to be suspended. Then what we have to do? We execute the call first, binary of decimal n by 2, and then I have the definitions of the subsequent operations. Print f, say d n modulo of 2. Okay. Understood? That means it basically works in a stack type of scenario. So when I am calling binary of decimal, say 15 or 14, here I suspend my print of 14, print 14 mod of 2. I suspend my I push this operation in a stack. I call binary of decimal 7. I put these print functions for corresponding these things of 7 mod of 2 in my stack. Okay. So in this case, in this way, what is happening? The thing is that I am pushing all these printing functions in my stack, and when I am returning, I'll take the first element from the stack and I execute. I will take the second element from the stack, I'll execute. And doing these things is basically allow you to suspending the operations which has to be performed when we are returning from the recursive call. Okay, you get this point? So this is the program, how we do these things. So this program is basically, if you look into the binary, print binary, what is happening in the print binary. So print binary, it takes a argument of n, then it returns if it returns if n is equals to 0. Okay. Otherwise, what it does, it will call print binary n by 2. Okay. It will call the print binary n by 2, and it will print f d n modulo of 2. Okay, understand? So doing these things, when I am writing the print functions following the recursive call, that means I am suspending the operations. Okay, I am suspending the operations, and the operations will be executing when the returns will be performed from the call function, which is calling functions. Okay, so if I move this print function at the top, that means I am executing the printing operation, then I am moving to the recursion call. But when I put the printing function at the after the recursive call, that means I execute the recursive calls. I am moving downwards here, and I will perform the print functions when I will return from my down towards the towards this column, towards this position. So that means I am in having a value of 14 here. Without printing, I step down. So this is basically my print. Here I basically step down. Here this is my print of 7. Sorry, this is my print of 7. I step down. So the printing will be performed when I am returning from the step down towards the up. Okay. So the last recursive call print will be executed first. The second last recursive call print will be executed secondly, and it will perform in the opposite order, in the reverse order. Okay. So that means I am pushing some operations after the recursive call. That means I am suspending the operations. When we return, that operations will be executed. Okay. Get it? You understand this point?
Yes, sir.
So if I execute that with a 25, that means if I execute the 25, say I am writing in short form 25, that means I'll print one here, 25 mod of 2 is what that will be printed, or I am writing the lower part, that it will be printed 1. Okay, and before that I will move to 25 by 2 means how much? 15, 12. Okay, then it will print 0 here, but before that it moves to f of 6. Then it will again print 0 here, but it will move to f of 3. Then it will print 1 here, but it will move to f of 1. So it will print 1 here, and it moves f of 0. And now the returns will be executed. Understand? In this way, the returns will be executed. And in my display, I'll first find the 1. So this first one will appear, then the second, then 0, and 1. Okay? Understand? So what I am doing, so whatever the operations regarding this f of 25, I push it in a stack. In a stack means I place some things on top of some things. Okay? I cannot remove the lower part unless I remove the upper part. So this print is pushed at the bottom. This print is pushed on it. This print is pushed over the part, and in this way, Okay? So to execute the sequence, I have to first eliminate the 1, then I have to eliminate this, then I have to eliminate this, then that, and in this way I will get the sequence of 1, 1, 0, 0, 1. Yeah. Understand? Get it? So we check the result. If we execute the program, that gives me 1, 1, 0, 0, 1. Okay. Now let's just take it. If I move it over the part, so here, Control P. That means I am not suspending my operations. I am first printing and then going for the recursive call and executing the program. I'll get the opposite order. So my order is something like that. So now I am not suspending my print operation. So in my present implementation, this print will be executed first. So I'll get 1, then 0, and 1, 1. Because this, now I am not suspending my printing operation. I execute the printing operation, and now I am going for the call. So the part that we get, yes. So this is the output of the present. Sorry, this is not the output of the present one. There are so many outputs. Let me. Yes. Okay. So this is the output of the present condition. Understand? So prints and then call. Print and then call. And the previous one is that call and suspend your print. Okay. Understand? You get this point?
Yes, sir.
Yes, sir.
Okay. So just keep in mind that when I am designing the recursive functions, then some operations I have to either perform before, or some operations I have to either perform after the call. So whatever the operations we are performing after the call, I am basically suspending the operations. Yeah, that will be executed during the return call. Okay, understand? Okay, and there is another example. We'll discuss this example in our lab session, and this problem will be taken care during the laboratory session. Okay, understand? So let me stop for the class. Okay. So any doubt? Any?
Yes, sir. Sir,
Any
one
doubt?
doubt is there.
Yes. Can.
Sir, I want to show my screen because I have done it, but I have used different method for the recursion to convert into binary. Can I show?
Let me stop the recording. Otherwise, it will take. Okay, you can show.